Hello viewers, myself Muniraju Naidu, Assistant Professor, Department of Computer Science and Engineering, working at Institute of Aeronautical Engineering, Hyderabad. So in this video, I am going to discuss about some of the CPU scheduling algorithms. So in the previous video already we discussed what is scheduling, scheduling criteria, and some scheduling algorithms like FCFS, SJF, priority, and round robin scheduling algorithms. We already discussed in the previous video. So let us look into this today's concepts. So this is the continuation of previous video. The scheduling algorithms like multi-level queue scheduling, multi-level feedback queue scheduling, thread scheduling, and multiple processor scheduling algorithms. See, multi-level queue scheduling algorithm. So we know how processor can schedule various processes. Basically, each and every queue we can call as a ready queue. That particular ready queue is divided into the different classes. So we have some queues like ready queue, waiting queue, device queues. So this particular ready queue is divided into the different classes. Each class has its own scheduling algorithms. In the sense, class in the sense, whether any particular process is related to the which class, like those comes under the foreground processes or background processes. So we know foreground processes are, we can call as a interactive processes. Always the user interacts with that particular task. Those are foreground processes. And background processes we can call as a batch processes. So by default the system can execute some background processes. So these two classes have a different scheduling needs. So for this kind of situation, we have this multi-level queue scheduling algorithm. So simply say that ready queue is divided into the separate queues for each class of processes. So whatever the queue, each and every process is permanently in a given queue. So each queue has its own scheduling algorithm. Each queue has its own scheduling algorithm. Let us take the top level queue is executing the process only in the round robin fashion. Then the next level queue executing the process with the help of SJF. Then the next level with the help of FCFS, like that. So here the scheduling must be done between the queues. In case of multi-level queue scheduling algorithm, here the scheduling must be done between the various queues. For example, here a fixed priority scheduling. Fixed priority scheduling. So that is, it serves all from foreground process, then from the background processes. Right? So automatically what happens? There is a chance for the starvation. Then time slice. You know, from the round robin algorithm, you know the terminology called as a time quantum or time slice. So each and every queue gets certain amount of CPU time, which it can be scheduled among its processes. Right? So within that particular time period, that particular process will complete its execution. So let us take 80% to foreground in round robin as well as 20% to background in FCFS scheduling algorithms. See, this is a simple pictorial representation of a multi-level queue scheduling algorithm. See here, this is the Q1. Let us take, this is the Q1, this is the Q2, Q3, Q4, Q5. So in case of Q1, only system processes are executing. In case of Q2, only interactive processes are executing. Q3, interactive editing processes. Q4, batch processes. Q5, student. Let us take any number of queues, n number of queues. But here one thing is priority. Always the processor gives some importance or priority to the Q1 processes. In the sense, first of all, whatever the process which comes under the Q1, so those processes are executing. Let us take P1, P2, P3. So P1, P2, P3 from the Q1 are executed. Then only it comes to the P4 from the Q2. So that is multi-level queue scheduling algorithm. What are the advantages of this multi-level queue scheduling algorithm? The application of separate scheduling for various kinds of processes is possible, because here the algorithm itself specifies that the queues, each and every queue is independent of the next one. So the system processes are executing with the FCFS, interactive process, SJ, batch process, round robin, student process, fixed priority based scheduling. So these are the various advantages of multi-level queue scheduling when compared to the previous algorithms. But what is the drawback? Here the lowest level of processes faces starvation problem. So because whatever the process which comes under Q5, like student process in our example, right? So what happens each and every time the processor schedules the process which is under the highest level. But what happens to the lower level process? Automatically there is a problem we can call as the starvation. Each and every process which comes under the lowest level, which faces that particular starvation problem, right? So let us look at this example, a multi-level queue scheduling algorithm. This is the example problem. So let us consider the below table of 4 processes P1, P2, P3, P4, which process comes under this multi-level queue scheduling algorithm. So here, in addition to the burst time, here we need to represent that queue number, right? So that particular queue number which specifies what is the queue of that particular process. See, this is the queue number actually 1, 1, 2, 1. So this is the burst time 4, 3, 8, 5. Right. So this is don't look at that. So this is the arrival time, that is 0, 0, 0, 10. Right. So for process P1, right, for process P1, this is arrival time 0 and the burst time is 4, that is the queue number is 1. For process P2, arrival time is 0, burst time is 3 and queue number is 1. P3, arrival time is 0, CPU burst time is 8, queue number is 2. See, in the sense, the priority of Q1, this is Q1, these two are Q1. So the priority of Q1 is greater than Q2. So whatever the process comes under the Q1, which uses the round robin scheduling algorithm. Let us take a time quantum is 2 milliseconds and the next level, that is a Q2, which uses the FCFS. Now based on these particular inputs, here we need to prepare the Gantt chart, right? See, let us take arrival time is 0. So what is the first process? According to the multi-level queue scheduling algorithm, whatever the process which comes under this particular Q1. So here the P1, the burst time of P1 is 4 milliseconds, right? Okay. So here this particular Q1 which uses the round robin algorithm. So what is the time quantum? 2 milliseconds. So within that particular 2 milliseconds of P1 is executed. So 2 milliseconds of P1 is executed. Now P1 is entered into the preemptive state because this is the round robin. So after the time quantum 2 milliseconds is expires, automatically the process is entered into the waiting state of the ready queue. Now what is the next process? P2. So the total CPU burst time of P2 is 3, but according to the time quantum which executes only 2 milliseconds. So P2 2 milliseconds. Now the P2. So first initially the P1 entered into the waiting queue. Now P2 entered into the waiting queue. So what is the 2? 2 plus 2, 4 completed. Now again P1, because this is the process which is in the Q1 only, right? Whereas according to the burst time also, P1 is having 2, P2 is having 1, P3 is 8 and P4 is 5. But here we don't consider the P3 up to now because this is the Q2, that is a level 2, right? So then again P1 is executed. So what is the remaining time? 2 milliseconds. So P1 again 2 milliseconds is executed. So now P1 is executed successfully. Now here we need to compare with P2 1 millisecond, P3 8, P4 5. Now we need to compare with P2 1 millisecond and P4 is 5 millisecond, because these two comes under the same level of queue. But which is the less one? So P2 is only 1 millisecond it takes. So now P2, it's time for P2 to execute. So 6 plus 1, 7. So now here up to this P2 is also executed successfully. Now we have P3 and P4. But P4 is at Q1, whereas P3 is at Q2, right? So what is the, we can call as a time, burst time of P3 is 8 milliseconds, right? So here P3 is executed up to the 3 milliseconds. After that, these two are equal. So now it's time for P4. P4 is 5. So 7 plus 3, 10. 10 plus 5, 15. Now P4 is completed up to now. What about the last one and what about the remaining time that is executed? So here remaining is a 5. So P3 is executed that particular 5 milliseconds. 15 plus 5, 20 milliseconds. So like this, a multi-level queue scheduling algorithm will works, right? So first of all, the processor fetches the process which comes under the top level queue. So this is the explanation regarding that Gantt chart. At starting, both the queues have processors, right? So process in Q1, either P1 or P2 runs first because of highest priority in the round robin fashion and completes after 7 units, then process in the Q2, right? So because after 7 units here, the process P3 comes into the picture because there is no process in the Q1, but while it is running, P4 comes in Q1 and interrupts P3. So definitely, and start running for the 5 seconds, and after its completion, P3 takes the CPU and completes its remaining execution time. So that deals about the multi-level queue scheduling algorithm. Then coming to the multi-level feedback queue scheduling algorithm. Multi-level feedback queue scheduling algorithm. We know feedback in the sense it's a cascading manner. One output may act as input to the next one, right? So a process can move between various queues. What happens here? The aging can be implemented in this way, right? We know the solution for starvation is aging, right? So here, any process can move between various queues like Q1, Q2, Q3. If any particular process is accepted by the processor in Q1, it is executed successfully. Or else, that particular process may not be waiting for a long period of time in the Q1, then it shifts to the Q2. So like that, this multi-level feedback queue scheduling algorithm is implemented. So multi-level feedback queue scheduler defined the following parameters. What are those parameters? First of all, number of queues. Number of queues, right? So how many number of levels are there? How many number of queues are there? Then scheduling algorithms for each queue. Scheduling algorithms for each queue. Then method used to determine when to upgrade a process. So what is the method we are going to use to determine whenever we need to upgrade any particular process? Then method used to determine when to demote a process. So this is very important. Upgrade as well as the demote a process. Then method used to determine which queue a process will enter when the process needs service. So because we have different levels of queues as well as the different types of process like foreground process as well as the background process. Now in this particular multi-level feedback queue scheduling algorithm, these are the basic parameters like how many number of queues are defined. Then what type of scheduling algorithms are used for each and every queue. Then what is the method we need to use to determine when to upgrade the particular process. Similarly, when to demote a particular process. Finally, what is the method we are going to use to determine which queue a process will enter when that process needs service, right? Because these are the solutions for various problems, right? See, let us take simple example. We have defined here 3 queues like Q0, Q1, Q2. So initially the Q0 that uses the round robin scheduling algorithm is time quantum 8 milliseconds, and so that is this is the Q0 which is uses the 8 milliseconds, and next one is Q1, which uses 16 milliseconds. So these two are comes under the round robin scheduling algorithm. Then Q2, which uses the FCFS. So this is 16 milliseconds. So this is a multi-level feedback queue. So automatically this input may acts as a output may acts as a input to the next one. So this output may act as a input to the next one. So here how the scheduling takes place. See, whenever a new job enters into this particular queue knot, any new job or new task, so which is served FCFS, right? So whatever the jobs, whatever the process entered into the queue, those are served as a FCFS. But when it gains the processor, that particular job receives only 8 milliseconds, because whatever the process which enters into that particular queue knot, the total time quantum is 8 milliseconds. So whenever that particular process gains the processor, the job receives only 8 milliseconds. Then what happens, round robin and time quantum already we discussed in the round robin scheduling algorithm. If that particular process doesn't finish within that particular time quantum, then again that particular job is moved to the next level queue. The next level queue. So that means, let us take simple example. One particular process which comes under the 10 milliseconds, which comes under this particular queue knot, right? So initially the processor taken that particular process and executes until 8 milliseconds, up to the 8 milliseconds. So that means 10 minus 8 only, which is having the 2 milliseconds. So now what happens, that particular process P1 enters into the Q1. So here process P1 is there, but the burst time of P1 is only 2 milliseconds. Right. Now at this particular queue, at Q1, the job is again served as FCFS and receives 16 milliseconds of time, additional milliseconds. Right. So there is a maximum limit is 16 milliseconds, but here the process execution time is only 2 milliseconds. For example, let us take the knot is 10 here, let us take 20. So what happens here, 20 means at first round 8 milliseconds are completed, then remaining 12 milliseconds are there. Is it right? So within that 12, 16, very good. So within that it completely executes that particular process. If it still doesn't complete, let us take here, 30 milliseconds. So what happens? 30 minus 8, definitely 22. So 22 is greater than 16. So if it still doesn't complete, it is preempted and then moved to the Q2. So here already 16, 22 minus 16, right? So remaining 6 milliseconds of P1, which is executed under the Q2. So this is a multi-level feedback queue scheduling algorithm, right? Multi-level feedback queue scheduling algorithm. So simple logic here, similar to our multi-level queue scheduling algorithm, there are different levels of queues. Each and every queue which is executed the process either by using any number of algorithms, like any type of algorithms like round robin, SJF or FCFS. So whenever any new job enters into the first level of queue, which is served based on the algorithm FCFS, so whenever the processor catches that particular process to execute, now it checks what is the time quantum. If within that particular time quantum the process is completed, it simply terminates the connection. If it is not completed, then the remaining time that enters with that particular remaining time that enters into that next level of queue. So this is a process until that particular process executes completely. See, this is the multi-level feedback queue. Already discussed that. This is the first level with the time quantum 8. This is the second level, time quantum 16. This is the third level, FCFS. See, this is the output of it acts as an input to the next one. So this is the output which acts as an input to the next one. Is it right? So that is a multi-level feedback queue scheduling algorithm. So what are the advantages and disadvantages of multi-level feedback queue scheduling algorithm? Here the basic advantage is low scheduling is overheaded. Low scheduling is overheaded. So each and every level of queue executes the process. If it is not completed within that particular time quantum, again it is shifted to the next level. So it allows aging, but there is no starvation. Right? It allows aging. So what happens here? There is no starvation. So multi-level feedback queue scheduling algorithm only solves the problem of starvation. But what is the drawback? First one is not flexible because it also requires some means of selecting values for all the parameters to define the best scheduler. So we don't know exactly which level of queue executes my particular process. So that is also it's the most complex one. Then coming to this thread scheduling. So this is a different concept when compared to the remaining ones. So basically thread is a lightweight process. A thread is a lightweight process. So generally threads are represented like this. Threads are represented like this. So we have single threaded process model, multi-threaded process model. So we'll discuss later these concepts, right? So, but here we need to describe this thread scheduling. So what is the difference between user level threads and kernel level threads? And whenever these threads supported, definitely threads scheduled as well as not the processes. So we have many models like many to one, many to one, many to many, and one to one, right? So these are the thread library schedules which user level threads to run on LWP. So which is known as a process contention scope. Process contention scope, because since scheduling competition is within the process, so this is typically done via priority set by the programmer. So we have here system contention scope, that is SCS. So generally kernel level threads scheduled within this particular SCS only, right? So we look into this what is meant by thread scheduling in deeper, right? See, we have see, for example, this is many to many threads, right? So this particular thread is mapped to this one, this particular thread is mapped to one. So we know one to one. So this is a one to one mapping. Similarly, many to one, right? See, basically this particular thread scheduling, which is either using P threads as well as the Win32.8s as well as the Java virtual machines like threads. So API which allows application programming interface which allows specifying either PCS or SCS during the thread creation only. So by default, this particular P-thread scheduling is generally used in the command line user interface operating systems like Unix. There previously we can call as a GNU's P-thread, right? So this P-thread scope process which schedules the threads using the PCS scheduling. Similarly, P-thread scope system which schedules the threads using the SCS scheduling, right? But this P-thread scheduling can be limited by the operating system like Unix, Linux and Macintosh operating systems only can allow P-thread scope system, right? So that's why here we can call as a P-thread. So this is the simple example for P-thread scheduling application programming interface. See here, include pthread.h, sto.h and define number thread 5, right? See, just like our process, whenever just a process is created, automatically the system can generate one PCB. Within that particular PCB, there are number of parameters like process ID, process name, process context, like that. Here, the process, the P threads, which creates that, see here, P-thread ID and P-thread attributes. Then it's get the default attributes and it sets the scheduling algorithm to either process or system, that is either PCS or SCS, right? So P-thread attribute set scope, that is the attributes, P-thread scope system. Then set the scheduling policy. Set the scheduling policy, either first in first out or round robin or some other thing, right? Then we need to create the threads. So like this, a P-thread scheduling application programming interface is scheduled. Then next one is multiple processor scheduling. So we know CPU scheduling is more complex when multiple CPUs are available. Definitely, nowadays we are using multitasking and multi-programming concepts. So CPU scheduling is more complex when multiple CPUs are available, right? So those are generally, you can categorize these homogeneous as well as the heterogeneous processors. So homogeneous processors within a multiprocessor. right? So basically this multiprocessing is categorized into the symmetric as well as the asymmetric multiprocessing. So we know what is meant by symmetric, same. So each and every processor is self-scheduling all the processors in that particular system which is common in ready queue. So what happens? We can call as at least in one private queue, all the processors comes under that particular private queue only. So that is a symmetric multiprocessing. Whereas asymmetric means different. Only one processor accesses the system data structures, remaining all the need for the data sharing. So like that, symmetric as well as the asymmetric multiprocessing is there. Then here the processor affinity. That means the process has affinity for processor on which it is currently running. Because I am having two processors. Right. At the same time, I am having 10 number of, I am having two processors like capital P1 and capital P2. But I am having the processors like P1, P2, P5 here. P1, P2, P5 here. Here, P3, P4, P6 here. So, the process has affinity for processor on which it is currently running. So, the P3, P4, P6 are currently running on the P2, whereas P1, P2, P5 currently running on the processor P1, right? So that is represented here, the processor affinity. See here, we know uniform memory access and non-uniform memory access. Non-uniform memory access and CPU scheduling algorithm looks like this. See, this is the system, memory, the storage area. This is the processor, right? See what happens in case of non-uniform memory access, and this is the CPU scheduling. So here the memory placement algorithms can only consider the affinity. So each and every processor can execute a number of processors, right? So whenever this particular processor communicates with any one of the processors which comes under this particular system, see that is this particular process access any data from this particular memory, then automatically it takes some time. So that is we can call it slow access. Slow access. At the same time, we can call it as a homogeneous, same, within the same. So the processor can access any data from this particular memory. It takes the fast access. So that is a non-uniform memory access as well as the CPU scheduling. Then multi-core processor. Multi-core processor. So you are very familiar about this core process, right? Single core processor, dual core processor. So what happens in case of single core processor means whatever the task we are going to execute, those tasks are executed in the serial fashion only. T1, T2, T3, T4, like that. Whereas in case of a dual core processor, right, first the task is executed at the first core and the next task is executed at the next one. Then next task T3, here the T4. So that means the parallel execution is done in case of dual core processor, right? So recent trends to place multiple processor cores on the same physical chip, that is very important, right? Dual core processor is nothing but on the same chip they need to embed that particular multiple processor cores. So it is faster and consumes less power when compared to the multiple individual processors. So multiple threads per core is also increased. So it takes advantage of memory stall to make progress on another thread while memory retrieve happens, right? See here, this is the example for multi-threaded multi-core system. Multi-threaded multi-core system. See, x-axis which we need to measure with respect to the time. Right. So here the C represents the compute cycle, whereas M represents the memory stall cycle. Right. So in case of single threaded model, what happens here? So compute cycle, memory cycle, compute cycle, memory cycle in the serial fashion. Whereas in case of multi-threaded multi-core system, see at this particular point of time, that is at 0th millisecond, first the compute cycle is executed. So before execution of this particular compute cycle, then the next one, then if any next process is there, then it executes on the another thread. So that is we can call it the parallel execution of multiple programs, right? So that deals about the scheduling algorithms, multi-threaded multi-core scheduling. Then virtualization and scheduling. So basically this virtualization software which schedules the multiple guests onto the CPUs, right? So nowadays we have a number of tools like AnyDesk, right? So we need to easily utilize other systems with respect to their permissions. So each and every guest doing its own scheduling, that is not knowing it doesn't owns the CPUs, can result in poor response time, can affect the time of day clocks in guest, right? So there is a virtualization and scheduling. So definitely we will describe this in the next later videos. So virtualization as well as the scheduling. Just here I am giving the introduction about virtualization and scheduling, as well as what are the various operating systems examples related to this particular scheduling, like Solaris scheduling and Windows XP scheduling, as well as the Linux scheduling, right? So each and every operating system which follows some different mechanisms as well as different procedures to schedule the various processes, like so in case of Solaris, generally it takes the tree based structure. Then we know Windows XP nowadays we are using this particular graphical user interface like Windows as well as the Linux, right? So with this I hope I complete this particular scheduling concepts, right? So in this video I'm going to already discussed about this multi-level queue scheduling algorithm, multi-level feedback queue scheduling algorithm, and multi-processor scheduling algorithm, and multi-core scheduling, and virtualization and scheduling. Finally, what are the various examples for related to this scheduling? I hope you understood. Take care.
Like, share and subscribe. Hit the bell icon for more updates.